All right, what's going on? Hello, happy Tuesday, and welcome to Advent of Code 2020, Day 8. All right, so let's take a look. Okay, this one is called Handheld Halting. Your flight to the major airline hub reaches cruising altitude without incident. While you consider checking the in-flight menu for one of those drinks that come with a little umbrella, you are interrupted by the kid sitting next to you. Their handheld game console won't turn on. They ask if you could take a look. You narrow the problem down to a strange infinite loop in the boot code, your puzzle input, of the device. You should be able to fix it, but first you need to be able to run the code in isolation. The boot code is represented as a text file with one instruction per line of text. Each instruction consists of an operation. Here we have ACC, JMP, or NOP, and an argument, which is a signed number, such as +4 or -2. Okay. ACC increases or decreases a single global value called the accumulator by the value given in the argument. For example, ACC +7 would increase the accumulator by 7. Okay, the accumulator starts at 0. After an ACC instruction, the instruction immediately below it is executed next. JMP, or jump, jumps to a new instruction relative to itself. The next instruction to execute is found using the argument as an offset from the JMP instruction. For example, JMP +2 would skip the next instruction. JMP +1 would continue to the next instruction. JMP -20 would go 20 lines above. Okay, NOP stands for no operation. It does nothing. It is a no op. The instruction immediately below it is executed next. Okay, for example, here's a program. Okay, and then these instructions are visited in this order. So we have no op, right, with +0 as an argument. It's the first one visited. Goes down here, the second one visited. This is increase the accumulator by 1, and then we step down, third visit. Okay, but now this is a jump, which tells us to go 1, 2, 3, 4, and so that's why this here is the fourth visit, which is an accumulator. Then we have jump -4. Okay, so that's going to jump back here, and then so there we could see where our infinite loop is happening, right? So jump 4 is going to take us here, jump 3 is going to take us here, and then we're back. Okay, so this is just kind of talking through the same thing that we just talked through. So that's your infinite loop, right? Is that it can never make it past this jump -4 to actually finish the program. So it's just going to keep looping forever. Cool. So basically in real life, this is definitely a lot more complicated in terms of a more complicated programming language. But here, we're just going to say the infinite loop is whenever some line is about to be run twice, right? So like we said, in normal programs, you're going to expect maybe a method or a line to be run multiple times. That's normal. But here, in this example, and in the context of this problem, anytime an instruction is about to be run for a second time, that's when we're going to say, oh, hold on, we're looping. Okay? And so this is saying immediately before this is going to be run for the second time, the value in the accumulator is 5. And so basically we're told, run your copy of the boot code and then tell us what is the value in the accumulator. Okay? And so here in this case, kind of just like the last one, I did go ahead and finish this ahead of time, but we're going to walk through it all. So here's our puzzle input. Okay, so it's just a really long program in this language. Cool, so today, as per usual, we're going to be doing this in Ruby. However, this is a really cool problem because this is what you'd call a stack-based language, right? And so I think some keys of stack-based languages are there's an implicit state that's being managed here, right? Which is sort of part of the program, but not in part of the code that is written here, right? We have this accumulator. So that's an interesting feature of this language, right? We're never assigning anything as the accumulator and saying that's what's being incremented. It's just sort of there. But what you could do, so there's a really cool language called Racket, which is a Lisp variant, and it's kind of, a lot of Racket is built around helping you write your own sort of problem-specific languages. So I'm thinking after we do today in Ruby, then there's a good chance that I'm going to revisit this problem and look at what would it look like to write your own language, to basically make this a valid programming language. And then instead of taking our input and parsing it in Ruby and doing things, we would just execute it as an actual program. So coming soon. But today we're just going to look at this in Ruby, okay? So great. So what are we doing? Right. So the first thing that I want to do is I want to start thinking about how I'm going to do this. So one thing I'm going to do is I'm going to parse my input, and then each part of my input I'm going to store as either the operation or the argument, and then I'm going to keep all of those things in a big list. Because I know that throughout my program I'm going to be kind of going up and down this list. So let's get started with that. So let's see. Let's get to Advent of Code 2020. Let's get into Ruby. And then let's create our file. So let's say touch day 8 live.rb. Okay. And then let's open that up. Okay, cool. All right, so what do we got? So the first thing that I'm thinking about is our instruction, right? Like we said, is an operation and it's an argument. So the first thing I'm going to do is create some structure to store that. And so I'm going to do something that I haven't done yet in Ruby, and that I don't do too often, but it's pretty nice, which is a struct. And a struct is sort of like a lightweight object that's a little bit nicer than a hash, because you could sort of treat it, it has accessor methods and getter methods, and so it looks a little bit more like an object than a hash, right? And it has some other nice features, such as, you have this definition up here where we're saying struct, and in here we're sort of defining what those keys are going to be, and those are the only keys that we're going to have in there. And so in that way, it's more constrained than a hash, and it can kind of make things a little bit more readable when we're trying to figure out, like, okay, we're pulling these keys out of this object, like what are the keys in the object, what does that look like? If it's just a hash, you don't really know, other than maybe throwing a debugger in there and inspecting it. Whereas with the struct, we're kind of constraining that, right? We're saying, okay, it has a field operation, which I spelled wrong, and it has a field arg. Okay. So now let's think about the next thing I want to do is I want to have, right, so this code is all part of a program. So let's say we're going to have a class which is a program. And so what does a program have? So a program, we initialize it with some input, which is going to get broken up into a set of instructions. So here we can say, let's just say parse input. We're going to pass in the input, and then that is going to give us a bunch of instructions. And so here we can say instructions, right? It's going to be one of the things that we have in here. And so what is that parse input going to look like? So here we go. Here, parse input is input. Okay, so let's take a look at what does our input look like, right? So it's, once again, we're breaking this down into individual lines. And then I think the parsing should be pretty straightforward, because we simply have something space something else, right? So we don't need a regex or anything here. We could just split on the empty line. And then the other nice thing is that Ruby is just going to handle the fact that this is a signed integer string. It's going to have no problem with that. It understands what plus and minus means in the context of turning strings into numbers, and so we don't really actually need to do anything special there at all. This should be very straightforward. So let's take a look at what that looks like. Okay, so we're doing input. We're doing not strip but split by new lines. And then what are we doing? So we're going to turn this into array. So we're going to map So this is a line. Okay, and now, so what we're going to do to get that, the op and arg, right, like we said, so op arg is line dot split by the empty space. One thing that I'm going to do, because I think one thing I'm noticing is you see here, I think there's an empty space after potentially. So I'm just going to make sure to get that out of there. Okay, so now when we split by this, so we know just because of, we know based on what our input is, when we split here, this is going to produce an array that has at most one thing in it. So I feel very safe doing this sort of split assignment. You don't see it too often, but it's available to you in Ruby. So there we go. So that's splitting. What else do I need to do here, right? I think all I really need to do is just make a new instruction struct with this. And so that's how I can do that. And so now parse input is going to return to me a list of instructions. Okay, cool. So now let's think about how we're going to do this, right? So we have our list of instructions. So basically we're going to have some code, and it's going to follow these instructions. It's going to do whatever, and then we need to keep track of when we're looping, right? So if we think about this, we're going to have, basically we're going to hold on to the index of the list that we're at. So I'm going to say, okay, at the beginning I'm at position 0. Run at position 0, and then, depending on what that code is, that's going to tell me how to increment or step to the next position in my list. And so in addition to that, I want to keep a track of all the positions that I've visited so that when I reach a position for the second time, then I can say, okay, I'm looping now, so then I can exit the program and report what's the value of my accumulator at this time. Okay, and so let's see, what would that look like? So let's say that we, let's see, so let's define a run method, right? Because we're running this code. So we're going to run. And so what I'm going to do here is basically, so there's a few different ways that you could do this, right? One way is that we could have the index, and then the accumulator is on our as part of our class, right? So let's just start with that simple way. Okay, so run. So what does run do? So run basically finds the operation at our current index, and then it needs to evaluate that operation, right? Okay, so what are we going to do? Oh, another thing that we want to do here actually is we want to keep track of those visits, right? And so let's say visits, right, is an empty array. That's how we initialize that. Okay. So when we're calling run, the first thing that we're actually going to do, so I'm just thinking about how we're going to do this. Run is going to be a recursive function, which is if there's no reason to exit the program, it's just going to call itself again. And at that point, the index will have been updated and we'll be running a new line. Right, so knowing that, what's, again, recursive, first thing I always think of is what's the base case. So the base case is that we have already visited the index that we're about to run. And so what we would do there is we're just going to return the value of the accumulator. So we're going to return ACC if visits, and here I can say, let's just add some more readers here, just because why not? Okay, so we're going to return ACC, visits, includes, didn't want to do that, the index, not just X, but the index. Okay, so here we return the accumulator if we've already visited this line. Okay, then what's the next step? So the next step is we're going to record this visit. So we're going to say, and that's just a reader. So if I want to add, so I'm going to say visits. We're going to add the current index that we're at. Okay. So then the next thing that we're going to do is we're going to say what is the instruction that we're about to run, right? So the instruction is that list of instructions at the current index. Okay, cool. So now what are we doing? So there's a second sort of, oh, actually no. No, all we got to do is run this. That's all. Okay, so let's say we're going to have a method called run instruction, which runs an individual instruction. So run instruction takes an instruction that it's running. Okay. And then what else do we do here? So, and then after that, we just call run again, right? Loop back around. And so, yeah, cool. So now let's define run instruction. What does run instruction look like? And that takes a single instruction. And so what run instruction does is different depending on what the operation is, right? So let's start a case statement on instructions operation. And then what do we have? So we have when, and I believe it's ACC, JMP, and NOP are our two things. So basically when ACC, when NOP, when JMP. And you know what? Let's just kind of alphabetize that, make that nice. Okay, so what do we do when it's ACC? So when it's ACC is we add whatever this argument is to our accumulator, and then we increase the index by 1. We just go right on to the next line. So basically our accumulator plus gets the instructions argument. And actually now that I'm thinking about it, where did we do this? So here, this one is actually, I forgot that we didn't turn that argument to an integer, so I need to do that. Okay, so again, so this is ACC, so our accumulator that we're storing here gets, plus gets the argument for our instruction, and then the index plus gets 1. Okay, and then that's all that we really do there. Now for JMP, here, in this case, it's just the index plus gets that argument, right? So, because we're going to jump, we're going to change our index to whatever that argument is for the jump. And then that's it. We don't do anything for the ACC. And then for the no operation, the index is just increased by 1. All right. So we don't even really use that argument at all, I think, as far as I can tell. I think it just gets an argument just because that's what the language requires, is an operation and argument, but I don't think that we actually use that for anything. Right, because it says NOP does nothing. Just goes to the next one. So we don't really care about the argument at all. Okay, and really, so that's kind of the heart of running this language. Right, and then just for, I always like to throw on just the else case. And I think that I've handled all of my cases, but maybe I'll get some input. And in that case, I'm just going to say unknown operation. And then I'm going to say, what is instruction operation? Okay. Cool. So, I think that that is all that we really have here. This is just yelling at me. Too many lines. So says Robocop. All right. So I believe that is actually all there is to it. So now let's get a test file going. So day live spec.rb, crier relative, day 8 live. Okay. And then what are we doing? So our spec is describing what? I already forgot what I call this thing. Okay, so this is just called program. Okay. And then, so let's get our input. Okay, that's going to go in here. And so here is our test input. Okay. Do some fun indenting here. Okay, and now we have our input. So what are we doing? So we're going to say it returns the accumulator right before the loop begins. Okay. And then here, so what we're saying is, so our program new with that input, and then we expect program dot run to equal, what was it? This is saying it's going to be 5. Okay. All right, so that's that. Let's see how that does. All right, so we'll close this down. Our spec day 8 live spec.rb, run that. Okay, that worked. Cool. So now what we can do is let's make our solution for this. Solution.rb, okay. I'm just going to copy some stuff from previous day. So here, this is day 8 live. This is day 8. Okay, great. And so now I could say my prog is a program new with my input. And then I'm going to put part 1 is prog.run. Okay. Ruby day 8 live solution.rb 1487. Okay. And now if I look here, the puzzle answer I submitted this morning correctly 1487. Okay, cool. So now we have something that can basically run this little stack language that we have here. So let's see what the next part is. After some careful analysis, you believe that exactly one instruction is corrupted. Okay, so somewhere in the program, either a jump is supposed to be a no-op, or a no-op is supposed to be a jump. No ACC instructions were harmed. And that makes sense, right? Because it doesn't seem like an ACC can actually cause an infinite loop, right? Because it doesn't really do anything. Although I suppose, you know, if they wanted to, a no-op and an ACC, in terms of how they affect the order of instructions being run, they're the same. So I guess an ACC could have been involved. But here they're saying, I guess to keep our lives a little bit simpler, we don't need to worry about changing one of the ACC instructions. It's going to be either a jump or a no-op. It needs to be swapped in order to get this infinite loop to be fixed. So the program is supposed to terminate by attempting to execute an instruction immediately after the last one. Right? So that's our sort of normal termination, is that we try to execute one more than the number of instructions we actually have. Okay? And here they're saying in this example, if you change the first instruction from a no-op to a jump, it would create a single instruction infinite loop, never leaving that instruction. Right? Jump 0, that makes sense. Okay? However, if you change the second to last instruction from a jump -4 to a no-op -4, then the program would terminate, right? And that makes sense because that jump that we talked about before when we were looking at the first part, that's the one that is leading to this infinite loop by jumping all the way back. And so that if we just change this, then we would go on to the last line, and then we'd go on to the one after that, and program's over. Okay. Cool. And so here it's saying, so if we did make this change to the instruction, the program did actually terminate. Then the accumulator would hold a value of 8 when it did terminate. So they're saying fix your program so that it terminates, and then report what is the accumulator after the program terminates. Okay. Cool. So let's see. If we go to our code, so what are we going to need to change here? And how are we going to solve this problem, right? So there might be some sort of clever analysis that it's possible to do. The approach that I decided to take is simply the brute force approach. We really don't have that many inputs to the point where that is problematic. Like, let's look at, what do we got? Day 8 input, let's get down here, 619 instructions, right? I mean, it's a lot. It's not a crazy amount, you know. It's not like millions to the point where this is going to take any significant amount of time to just simply go one by one and try. Like, okay, what if I swap this no-op? What if I swap this jump? Just don't be clever about trying to pick which ones you're going to swap and see what happens. Just try them all, and then once you find one that works, then you can stop. So that's what I'm going to do here. But there's a few things that we need to sort of think about how we're going to change here. So one thing is I'm going to be going through this program. I'm going to be changing the instructions. Well, I'm going to want to run a changed set of instructions, but while still maintaining what's the original set, right? Because I'm going to make a change, and then I'm going to run the changed version, and then if that works, then I'm done. If it doesn't work, then I'm going to undo that change and go on and do the next change. Right. So I want to maintain a sort of an unchanged list. And what does that look like? And then so that's really my main thing. So basically I'm thinking that I want to kind of pull out this instruction parsing into some other class that's going to run a bunch of programs, but there's no reason for me to parse the input over and over again here, so I'm just going to kind of pull this out. And so what is this? Let's say that this is a program checker, right? Because or debugger maybe, or fixer. Fixer, why not? Program fixer, because it's going to fix our program. And so what this gets initialized with, so we can say this gets initialized with input, and then really this, we're going to change this to getting initialized with instructions right off the bat. So that's just instructions. And then we're going to go down to this parse input method, and we're going to pull that out of here, and we're going to put that up here. Okay, so this program fixer is going to parse our input, and this is just going to feed it to that program. Okay, so here we could say instructions is parse input. Okay, and so now what are we going to do? So here, let's say, what are we going to do? Let's just call this run again, right? There's no real reason to call it anything else. Okay, and then how does this work? So running our program fixer, so we're going to go through our instructions, and we have to figure out, so one no-op needs to be swapped for a jump, and one jump needs to be swapped for a no-op. So what I'm thinking about here is go through each of our instructions. If it's an ACC, accumulate, just skip it. If it's a no-op, swap that with a jump, pass off those instructions to a program, run it, see if it has halted or if it's looped, and then, continue on. So one thing that I need to change is when I run my program right now, it's only ever going to return me some value when it loops. But if it halts, basically it's going to break right now. If this program didn't just loop, then this would not work. Right? So how do we handle halting? So what we said was the end of the program is when you try and run one more instruction than you have. And so what that would look like is here. So return ACC if instruction is nil, right? So if we try and get an index one larger than the total size of our instruction set, then instruction is going to be nil here. So we're going to return our accumulator at that point, right? Because that's what our answer is. However, there's one more issue here, which is when this function returns, it's going to return to me the accumulator no matter what. But I have no indication or no way to know whether or not are you returning me the accumulator because of the looping condition or because of the halting condition. And so one thing that I'm going to do here is just change this so that it returns me a hash, and then so it's also going to give me a reason, right? A reason that it is returning some value. So in this first case, the reason is that it looped, and then here in this case, so we're going to say ACC is that, and the reason is that it halted successfully, right? We made it to the end of the program. So that's that. Okay, and so now in order to just make sure that this still works, we're going to get the ACC out of there, and then here, once again, we're going to pull out, right, because now run is returning a hash. So let's just make sure that that still works. So we can run this. No, that doesn't work. Okay. Undefined method operation. Right, because my program is no longer parsing its own inputs. So that's why that's not working. So how can we fix that? Well, what we can do here is we can tell program fixer has a reader, instructions, right? So now I'm just going to say fixer new input, and then this gets fixer.instructions. Okay. So now I'm just sort of outsourcing the parsing of instructions to this new program fixer class. So let's see, does that work for the tests? No, it does not. Okay, given 0, expected 1 for parse input. So what do we do here? Well, we didn't give any arguments to parse input. That's a problem. Okay, let's try this again. Okay, great. Test passing again. Cool. And then we're going to actually need to do that here also. Fixer new input, and this is going to be fixer.instructions. Okay, and so now if I run this, cool, 1487. Okay, so now we can happily continue to work on part 2, knowing that our part 1 code is going to continue to work. We're not going to break that. Okay, so let's take a look at what does this run look like. Okay, so like we said, we're going to go through each of our instructions. I'm going to use with index here because in order to tell have I run this instruction before, I'm going to keep a record of those instructions that I've run. Or sorry, not that's the first part. Here, the reason I need the index here is to know which ones I've changed. Sorry, not which ones I've run, but which ones I've tried to change so that I can ignore those in the future. Okay, so let's say this does, that's an instruction, that's an index, okay. Okay, cool, so now what can I do? So, inside here I'm going to do another case statement on what is the type of instruction, or rather what is the instructions operation. And then so I have when it's a no-op, I'm going to do something. When it's a jump, I'm going to do something. In all other cases, I do nothing. So I'm not going to handle those. Okay. So what do I do here? So basically, when it's a no-op, I want to swap that for a jump, run the program, and see if it halts. So how can I do that? So my instruction is going to be, or rather, I'm going to have basically a copy of the instructions that I'm going to use here, right? I want to maintain my original set, so I'm going to make a copy. So here I'm going to say, sorry, I have a reader there, so I don't need that. Instruction, oh, I don't need this either. Okay. So here, make a copy, so instructions, duplicate. And then what am I going to do with my copy is I'm going to adjust this specific part. So instructions, copy at this specific index where I am is, so what are we going to do? We're going to introduce, add a new instruction there. And so that is instruction new. So the opposite of this one in this case is jump. But then I'm going to keep the original argument here. So that's going to be instruction.arg. Okay. Because the only thing that I'm swapping is the operation, not swapping anything about the argument. Okay, so now I have my copy, so then what do I do? So I'm going to get some results from creating a new program with these instructions, copy, and then running that program. Okay, and now here, this is where I can check my result. So I can say if result reason is that it halted, that my fix worked, then what I'm going to do, so I'm going to return results accumulator. Right? I want to return what is that accumulator. Okay. So now my JMP case is going to be exactly the same. There's probably some way that I could clean this up since it is so similar, but I'm a little bit lazy right now, so I'm just going to copy and paste. So basically, when it's a JMP, do the same thing except add a new no-op instruction. Once again, run that, return it if it halts. So I believe this is actually all that we really need in order to sort of brute force a solution. And again, this really only works because we know that it has to work. Like we've been told that there is one thing that you can swap. You wouldn't be able to do this sort of on something in the wild without knowing that information about it. Okay, and then what I'm just going to do here, just in case, this should return something, but just in case, let's just report no halt found. If for some reason our program doesn't work and we go through all these instructions, running the program every time, and at no point does it actually ever halt. Cool. So now I can go in here. I'm going to go into my tests, and I'm going to set up it fixes the program and returns accumulator before it halts, right? So now here we're going to say fixer is program fixer.new on that input. Fixer, we're going to say expect fixer.run to equal, and what do we expect it to equal? We expect this to equal 8. Okay, to equal 8. There we go. Let's run this. So that's rspec day 8 live spec.rb. Do that. 2 examples, both passed. Okay. So now let's go into our solution. We could say puts part 2 is. Now here we're going to do fixer.run. Okay. And let's run that. And here we go, 1607. And the puzzle answer that I submitted, and which was correct earlier this morning, is 1607. All right. So there you have it. That is day 8 in Ruby. Like I said, this is, working with stack-based languages in Racket is a lot of fun. So I think there's a very high chance that coming soon is going to be a series where I kind of walk through solving it that way. But for now, that's it. And I will see you on day 9.